Hello everybody. So let us continue with the Debye analysis. Now that we know that the number of modes with frequency between nu and d nu, that is g nu d nu, actually turns out to be something like 12 pi v nu square d nu divided by v0 cube. So considering that there is an average velocity associated with these normal modes of vibrations within the crystal, okay, monatomic crystal that we are considered. So given this, we also know that g nu d nu must also be such that between 0 to nu d, that is the maximum possible frequency of those collective vibrational modes, and that is, when integrated, the total number of modes should be 3n minus 6 or 3n when n is very large, okay, for convenience. Now given this, if we just substitute it, and then that becomes nu cube by 3, and 3 gets cancelled, so this actually becomes 4 pi v, and then nu becomes nu d, the upper limit, nu cube, and then v0 cube, considering v0 is constant value. And from here then we can substitute, just do the analysis, then nu d, that is the Debye frequency, we can have an estimate of Debye frequency, and that turns out to be 3n by 4 pi v to the power 1/3 v0. So you see that n by v, that is the number density, okay, number density of particles in the crystal. The density data if you have, and if you have for a crystal, say sodium crystal or say any other crystal, then if you have this data and also the density of the particles in the crystal, then you can have an estimate about the maximum frequency, and that is the Debye frequency associated with these vibrational modes in a crystal. And one can show that for such data being available, you can see that theta d can be defined. So theta d is nothing but h nu d by k. Remember theta e, that is the Einstein temperature, and in this case it is then the Debye temperature, which also has the dimension of temperature, that is Kelvin, and this k is Boltzmann constant, okay. So then we can actually have a data that for sodium, theta d for sodium metal, and that turns out to be 150 K, okay. And for say for example silver metal crystal, then it becomes 215 Kelvin, and for aluminium, just for record's sake, that is for aluminium it is 390 Kelvin, and for carbon diamond, and this turns out to be 1860 Kelvin. So you can see that as you go down this, we find that your nu d is becoming larger and larger. For diamond it is the maximum, and maximum frequency means minimum wavelength, right? So that means the smaller you can go from 0 to some value of frequency which are available, and that this being more strongly bound atoms in the crystal, they have relatively shorter wavelength waves associated with it. Now given this, and with this result, we can actually substitute and make it look little bit more convenient. in this manner, expressing this in terms of nu d cube. That means we can substitute this expression in terms of nu d now, and that becomes this nu square d nu. For this is for 0 to nu d frequency, and this is equals to 0 for nu greater than dy frequency. Now given this, we can now go back to Einstein analysis, and in the Einstein analysis, if we recall, then Cv equals to k 0 to infinity h nu by kt whole square e to the power minus h nu by kt g nu d nu, and divided by 1 minus e to the power minus h nu by kt whole square. So that was the expression. Now remember, in Einstein's case, this g nu became a delta function, so solving this integration was very easy. Just integrands was where nu was there was substituted by nu e, and that led to a Einstein result. But in this case, you do not have that simple result, so this expression remains, this integration remains in the expression. And then what we do now, we substitute this g nu with this. So then the expression becomes, you can work it out, so 0 to nu nu d, right, frequency, so this is nu d, and then h nu by kt whole square as it is remains, e to the power minus h nu by kt also remains, and g nu becomes 9n by nu d whole cube, and then nu square d nu, and this is divided by, as it is, h nu by kt whole square. Right? Now let us do a substitution. So let us do a substitution that h nu by kt, let this h nu by kt is x, then d nu would be replaced by what? kt by h dx, right? So we'll substitute d nu by this, and then this becomes x square e to the power minus x, 1 minus e to the power minus x whole square, and something else. So then that becomes 9nk, and then nu d cube, okay, and then once it is x, then when nu equals to 0, x is 0. When nu equals to nu d, x is h nu d by kt. So the integration now changes to h nu d by kt for x, and then it becomes x square, then e to the power minus x by 1 minus e to the power minus x whole square, right? And then this part I have taken out, so nu square d nu, and nu square, if you substitute x square and then kt by h, so kt by h whole square and x square, and then another kt by h dx for d nu. So if we bring it out, then that becomes equals to 9nk, and then kt by h cube, right? Now kt by h cube, and so kt by h nu d cube. And as we said, if you remember that theta d equals to h nu d by k, so that turns out to be t by theta d whole cube, right? T by theta d whole cube, that part becomes, and then what remains is, and this becomes theta d by t, so integration becomes theta d by t, d by temperature by the temperature of the system, and then x square, so it becomes x to the power 4 e to the power minus x by 1 minus e to the power minus x whole square dx. I hope this is what it is. Yes, so this becomes like that, and then this can also be written as, so this can also be written as just 9 in K.